These are the single-digit numbers, these are the double digits, and after that come the triple digits. But this assumes that we're using the typical digits 0 through 9. We could replace 3 with the value 13. Although this looks like two separate symbols, so let's squish them together to make a B. So now we have these single digits, these doubles, and then the triples. Notice this outlier. It used to be 103, but now it's 9013. It's a double digit that's larger than 100. And it's not even the largest. If we scroll down, we see this, 13d13, which equals 143. These extended double digits are cool, but there's a problem. Near the top of the table, some numbers are gone. We are unable to write 31. There's no 36, there's not even a 3. But wait, there's a fix. We can, ow, my knee! We can replace the digit 9 with -1. Again, this looks like two separate symbols, so we should squish them to make an L. So now these are the single digits. 9 is missing, but that's okay, because we can write it as a double digit. This is 10 minus 1. It's similar to how we write 9 romantically. So we can fill in the missing 9, and we can also fill in the missing 3. The 10's place is -1, and then the 1's place is 13, which add to make 3. Let's fill in the rest of the double digits. We still have some gaps in the 30s, but they get filled in as triple digits, such as -100 13d2. And it turns out these digits can represent all integers. And when I say all, I mean positive and negative. Our typical 0 through 9 can only represent positive integers. In order to write something negative, we need this extra piece. But our new set of digits doesn't need anything extra. We can write this as -1013. And so we'll say this set is plentiful. It can write every integer. But what makes it plentiful? It needs to have both positive and negative digits, but that alone is not enough. Each of these sets has a mix of positive and negative, but only one of them is plentiful. Can you tell which one? In this video, we will discover the properties of a plentiful set, learn how to check if a set is plentiful, and we'll explore a bunch of fun examples. To figure out which set is plentiful, let's try them all out. We'll start on the left. We've seen these digits already, except for 22. As usual, it has separate symbols, so we need to squish them. It looks like this fancy Z. So using this set, we get these single digits, these double digits, and then the triples. Notice, this lum is completely empty. We're missing 5, we're missing 15, we're even missing -1825. And this is because we only have 9 digits, so we can only fill 9 lums. To understand why, let's look at this lum. Every number ends with a 1. Here they all end with 20, and here they all end with 13. The endings are based on the single-digit numbers. If we start with some digit, we can move up or down by multiples of 10, which won't change the end digit. But moving left or right does change the end digit. Each end digit is stuck in its starting lum. So in order to fill all 10 lums, we need to start with 10 digits. Well, we need at least 10. But what if we use 11? Let's bring back the digit 2. This set is plentiful, but it creates a new problem: duplicates. 142 is equal to 120, and it's also equal to -100. There are a bunch of ways to write the same number. This set isn't plentiful, it's extravagant. And this happens with any set of 11 digits. Let's think about the triple-digit numbers. The count of writable numbers is 11 cubed. We have 11 options for each digit. If m is the minimum digit, then m and m is the minimum triple. And if n is the maximum digit, then n and n is the maximum triple. Every triple must be between them, so their difference is the count of unique values. Let's pull out the 111 and then make it ugly. Now we see a third power on each side. This is because we used the triple digits. We get fourth powers with quadruple digits, fifth powers with quintuple digits, and so on. The left has powers of 11, so it grows faster than the powers of 10. Eventually, the left will be larger. There will be more writable numbers than unique values, so we will end up with duplicates. And this would also happen if we used 12 digits or 13 digits or any other amount greater than 10. So to summarize, a plentiful set must have exactly 10 digits. If there are less, we'll have an empty lum, and if there are more, we'll have duplicates. So returning to this question, the left set only has 9 digits, so it's not plentiful. But the others both have 10, so we need to dive deeper. Let's look at the right set. It has a new digit, -99. And this looks like 3 separate symbols, so we really need to squish them together into a scooter. This set makes these single digits, these doubles, and these triples. There's a lot of gaps. Even the number 1 is missing. Let's try to write 1. It should be some string of digits. 1 is in the scooter lum, so the end digit must be scooter. But what digits come before that? Let's subtract scooter from both sides. That zeroes out the end digit, and on the left, 1 minus -99 is 100. We can divide both sides by 10, and we now have a new question. What is the end digit of 10? 10 is in the 0 lum, so it must be 0. Then we can divide by 10 again, and we end up with 1. But we've seen this question already. 1 is in the scooter lum, so the next digit is scooter. Then we subtract and divide, and the next one is 0, and then scooter, and then 0, and then scooter, and then 0, and then scooter. This will just keep going. But we need to stop at some point, or we'll end up as a scooter addict. So we can't write 1. This set is not plentiful. And so back to this problem, we know the left and right are not plentiful, so it must be the middle. But how do we know for sure? This set has -109, 4 separate symbols. We'll squish them to make a scooter. This set makes these singles, these doubles, and these triples. We're still missing 1. Can we write 1? It's in the scooter lum, so the last digit must be scooter. Then we subtract and divide to get 11. 11 is also in the scooter lum, so that's our next digit. Then subtract and divide to get 12, which is in the zoo lum, so that's the following digit. And if we subtract and divide once more, we get -1. That's the final digit. If we subtract and divide again, we just have 0. So we can write 1 as -1000 hundred scooter-de scooter. And this digit finding process can help us to prove this set is plentiful. While trying to write 1, we solved a sequence of numbers, ending at 0. This 0 is the key. In the earlier case, when scooter was -99, we went back and forth between 1 and 10. This sequence never reached 0, so we didn't get a result. So these steps are good. They move closer to 0. If all the steps are good, we'll eventually reach 0. But we need to watch out for these steps that move away from 0. They're the ones that can cause an infinite loop. If we have some bicycle, then we go to the next step by subtracting the end digit e and dividing by 10. We'd like the new digit to be closer to 0. It should be smaller. Well, to account for negatives, the absolute value should be smaller. If we do a little algebra, we find that bicycle is greater than absolute e over 9. If this is true, we will be closer to 0. But if it's not, then it's potentially infinite. We need to check these cases. And notice this depends on e, the end digit. They all have different values, but absolute scooter over 9 is the largest, so it will cover every other case. We need to check numbers of size 12 or less. The range -188 through -122. We already saw most of them, and it's easy to find the rest. So we can write everything in this range, which means that starting with any bicycle, we will have good steps that get closer to 0 until we reach a small number, which we know will end up at 0. So this set is plentiful. We can write every integer. And now we have this formula for the potentially infinite range. Let's apply it to the typical digits. The biggest is 9, so we get absolute 9 over 9. That's just 1. We only need to check a few values. 0 and 1 are fine, but -1 is not writable, not without its precious hyphen. And therefore, these typical digits are not plentiful. But that's okay. We have our new set, and we can mess around with it even further. Let's replace 6 with 86. Squish them together and we get raisins. That's short for wet raisins. And let's notice that absolute raisins over 9 is less than absolute scooter over 9. So we have the same range for potentially infinite bicycles. We already checked all these numbers, although some of them used the digit 6, which has been replaced. But that's okay. We can write 6 as -1,720 raisins. And -4 can also be written. So this set is plentiful. We can also replace 8 with 88. These squish to make raisins. That's short for wet craisins. Absolute raisins over 9 is also less than absolute scooter over 9. So we still have that same range. We just need to recheck everything that has an 8. It turns out they all have raisin representations. So the set is plentiful. It's pretty easy to make replacements with small numbers. But what about something bigger? What if we swap 7 for -3013? Of course, we need to squish these to make a 64th note. And then notice that absolute over 9 is 334.8. So now we have a much wider range of potentially infinite values. We need to check everything from -million, 1300,000, 100 raisins, all the way up to -billion, 20,000 scooter million, raisins, thousands, 20,000 13d4. That's a pretty big range. So I had a computer check everything, and they're all writable. This set is plentiful. So now we understand what you need for a plentiful set. 10 digits, with 1 digit per lum, and every small bicycle is writable. This is pretty cool, but honestly, I really made this video to get you comfortable with weird digits in base 10, so that you'd be prepared for weird digits in other bases, like 2, 12, 16, or 2 plus I. That's right, we can have imaginary bases, and they make fascinating patterns. But that'll have to wait for the next video. So yeah, thanks for watching, and thanks to the recent supporters of the channel. That's all that I had to talk about. So I guess unless anyone else has anything, we can end it there. I'll give you all a few minutes back. All right, thanks everybody. Bye.